Good morning, good afternoon, good evening, folks, for wherever you've joined us from for today's webinar on VisualCAM 2015 for SolidWorks. VisualCAM 2015 for SolidWorks is a Gold Certified CAM partner product that runs within SolidWorks 2010 all the way up to 2015. VisualCAM now offers both milling and turning modules, and in this webinar today, we will go through both the milling and turning features offered in VisualCAM 2015 for SolidWorks. Let us go ahead and bring up SolidWorks 2015, and upon loading SolidWorks, you will notice that the welcome dialog appears right inside SolidWorks, and which gives you access to useful resources for your online help, quick start tutorials, in addition to datasheet and what's new in VisualCAM 2015. Now, without any further delays, I am going to go ahead and close out of this dialog and load a part in SolidWorks so we can take a look at how VisualCAM integrates into SolidWorks and take a look at our milling module to start with, and we'll go through all of the different milling methods starting from 2-axis all the way up to 5-axis. Now, once you bring in a part into SolidWorks, you will notice a VisualCAM 2015 tab that appears right in your command manager. You can switch back and forth from your feature manager, features sketch tree, and also VisualCAM by just a click of a button. Now, VisualCAM also shows an entry right next to your feature manager design tree, and you can toggle from the feature manager design tree to the VisualCAM 2015 browser by just click of a button. The VisualCAM's interface shows 2 browser windows. We have the Machining Operations browser right at the top, and then the Machining Objects browser over down below here at the bottom of the window. Now, the Machining Operations browser has 2 main tabs, Program and then Simulate. The Program tab has 3 main groups. You have Machine Setup, Stock, and then Machining Operations. The Machining Objects browser down below has 4 tabs. Tools, where you can create, define, load tools from your library, machining regions, machining features, and also knowledge bases. First, we'll go up to the Program tab and we'll program the part that's currently designed in SolidWorks. Now, as this part that we model is prismatic in nature, where there aren't any sculpted bottoms or drafts on the part, parts like these can be easily programmed using 2-axis milling, or also known as 2.5-axis milling, where the Z remains constant as the cutter travels in X and Y. First, we will go out to the Program tab, and then in the Machine Setup group, we'll select Machine Tool Setup. The first thing we're going to do under the Machine Tool Setup is to establish the Machine Tool Coordinate System. By default, VisualCAM automatically orients the Machine Tool Coordinate System to the same orientation as the coordinate system in SolidWorks, which is aligned to the World Coordinate System. Now, if the part you modeled is in a different orientation, rather than having to remodel the part or reorient the part, you could reorient the coordinate system using the controls available in the Machine Tool Coordinate System. For example, I could spin it by an angle using the spin angle and the coordinates to reorient your coordinate system. Now, in this particular example, I'm going to align it to the World Coordinate System. The next step is to define the machining process in here. So we go to the Machine Tool Definition tab and set the machine type to be 3-axis. So for 2 and 3-axis application, we would pick 3-axis. For 4 and 5-axis applications, you can choose from 4 and 5-axis for the number of axes. We will now pick OK, and the machine type now appears under the machining job. Next, we'll go ahead and select the post processor. VisualCAM's mill module includes posts for over 300 plus machine controllers, which covers a wide range of CNC machines that are out there. Now, for this particular example, I'm going to pick Haas as my current post processor and then set my posted file extension to .nc. Additional posted file extensions are available depending on what your machine controller expects for it. We'll pick OK, and you'll notice that the posted post processor is now listed under the machining job. Next, we would like to go ahead and create our stock geometry. We'll select stock and then pick box stock. the system automatically computes a minimum stock geometry based on the bounding extents of the designed part and gives you the recommendation for the length, width, and the height. I could go ahead and change any of the parameters in here. So for this particular part, I'm going to add some thickness to the stock, so change my stock height to 2.25 inch from being 2.25. I can then click on Show Stock Visibility, which displays the stock model right around the part. You can see that the stock definition is also listed in the machining browser. So you can toggle the display of the stock visibility by just clicking on Show or Hide Stock Visibility from your machining browser. Next, I would like to align the stock to the part. So I'm going to click on Align Stock. And as the part we modeled here has a planar surface at the bottom, I would like to have the stock flush to the bottom face of the part. So for the Z alignment, I'll pick bottom, and center for X, Y, so the part will be centered in X and Y around the stock block. Next, I would like to go ahead and select the material for this process. So I'm going to be working with aluminum 6061, so I'll pick aluminum 6061 from the list of available material types, and then pick OK. Selecting material texture visibility displays the material texture on the stock geometry. Now, selecting a material also helps you in determining feeds and speeds for the operation you're trying to program. Now, if you look under the Tools tab, we already have certain tools that are defined in here. I could click on Create Edit Tools to edit or add new tools to my library, or I could load tools from my library. You can define your tool geometry, the tool properties, as well as feeds and speeds for each tool. Selecting Load From File allows you to determine feeds and speeds based on the stock material, tool material, surface speed, feet per tool diameter, and number of loops. Now, since we already have some tools defined and loaded from our library, I will go through the process of programming this part. In the next step, I would like to establish my work 0, or also known as work coordinate origin or program 0. So I'm going to pick work 0. For this particular part, I would like to establish my 0 to the top face of the stock blank, and I'll pick the southwest corner. So to do this, I'm going to click on Set to Stock Box. For the 0 face, we'll pick highest Z. And for the 0 position, I'm going to use southwest corner, and then pick Generate. You will notice that the work 0 is now transformed to the top of your stock and the southwest corner, and the work 0 appears under the machining browser. Next, I would like to face the stock down to the top face of the part. So for this particular process, I'm going to use 2-axis and facing. Other 2-axis operations are available in here, and we'll try to go through the other pocketing and profiling operation as we try to program this part. So we'll pick 2-axis and facing. This displays the facing operation dialog, and the very first tab is where you define the control geometry, where you pick the areas that you'd like to face. I'm going to click on Select Drive Containment Regions, and this automatically displays the Selection Property Manager. So I'm going to go pick the face edge, right-click on it, and pick Select Loop, which automatically selects a chain of face edges in SolidWorks for the features we would like to face. And I'm going to accept my selections, and these selections now automatically appear in the Control Geometry tab, and as you select each of these face edges, they're highlighted on the model correspondingly. In the next step, I would like to go to the Tool tab and select a face mill for this operation. And the Feeds and Speeds tab, I'm going to use Load From Tool. For the clearance, I'm going to pick Automatic, so this basically defines the safe transfer motions, the safety plane, or the clearance height for all your transfer and non-cutting motions. We'll pick Automatic, so it'll automatically clear the maximum stock or the part height, whichever is higher. The next tab is Roughing, where we'll specify the tolerance, the stock allowance, pick the cut pattern, the cut direction, step over, and then in the Cut Levels tab, you can specify the total cut depth. So I'm going to set my total depth as a 1/4 inch, as the stock is a 1/4 inch larger than the part in height. And I would like to program this in 2 levels. So I'm going to specify the depth per cut as 1/8 of an inch. And then I would go to the Entry and Exit tab to specify my entry and exit parameters. And I would like to apply these for each of those cut levels, and then pick Generate. Now this basically generates your facing toolpath, and the toolpath is now displayed on the graphics screen. You can toggle the toolpath visibility by selecting Show or Hide Toolpath from the base of the machining browser. You can also view the toolpath as you step in levels. We would now like to run a simulation, so we'll switch over to the Simulate tab, select the 2.5 axis facing operation, and pick the play button to run a material removal simulation. Now, during the simulation process, you can toggle the texture visibility on or off. Additional simulation controls like pause, simulate, and are also available in here. Once the operation has been simulated, I'll switch back over to the Program tab so I could now program the next step, which would be the pocket in here. So I'll go up to 2-axis machining and select pocketing. Now I would like to select my drive geometries in here. So I'm going to click on Select Drive Containment Regions and go pick the face edge on the geometry by clicking Select Loop. And I'll pick on this arrow to flip the face edge that I would like to select from the model. Accept the selections in here. And the selections are now accepted, and they're all listed under Drive Regions. For the tool, I'm going to go pick the 1/2 inch end mill. Feeds and speeds, I'll use Load from Tool. Clearance, I'm going to use Automatic. Under cutting parameters, I'm going to set my tolerance to 1000 and stock allowance to 0. So I would like to go and finish right to the edge of this pocket. There are several cut patterns you could pick from, and I'm going to use Offset as my cut pattern. For the step distance, I'm going to use 40% of my tool diameter. Under cut levels, I would like to determine the depth from the 3D model, so I'm going to use the pick button in here and select the top face and then the floor of this pocket. So that defines the total depth as a 1/4 inch, and then I'll pick Generate to create my pocket toolpath, and there's your toolpath right there. Now let's switch to the Simulate tab and click Play to run the simulation. You can also select Pause and then Simulate to End if you wish to run through the simulation. Now we already programmed a facing and a pocketing operation. I would now like to program the pocket with the island around it in here. So to do this, I'm going to repeat the same pocketing operation. To make it easier in here, I would like to copy this operation. So right-click on the pocketing operation, select Copy. Right mouse button click again and select Paste. So this basically creates a copy of the same operation in here. I would now like to edit this operation. You can do a right-click and select Edit, or you can do a simple double-click on the operation to edit it. Since I need to select these features on the pocket, I'm going to click Remove All and go back and select Drive Containment Regions. Right mouse button click on the edge and pick Select Loop, similar to what we did on the previous operations, and right-click on the island edge and pick Select Loop as well. So we would now select the two areas as the Drive Containment Regions. And the two regions are now listed under Drive Regions under the Control Geometry tab. Next, we'll use the same tool. We'll skip the process of defining feeds and speeds and clearance, as we would like to go with the same parameters as we had on the previous pocket operation. Now, under the cutting parameters, I would like to select Clean Corners. And in the Cut Levels tab, since the depth is different from the previous pocket operation, I'm going to pick the depth by selecting the top face and then the floor of the pocket. So you see that the total depth is 1 3/4. I would now like to step this in multiple levels, 0.35 inches per cut. You will notice that the island on this part is at a much lower Z level than the top face of the pocket. So I'm going to use this feature called Clear Island Tops and then pick Generate. So the system will automatically add a toolpath to clean up the island tops. If you take a look at the toolpath in levels, you'll see that there's a toolpath at 3/4 of an inch in here, which clears the island top. You can step through each of these Z levels on the toolpath until you get to the floor of the part. And run a simulation in here, so we'll hit the play button, and there's your simulation. You can always increase the simulation speed. You can always hit the pause and do Simulate to End if you'd like to run through the simulation. Now there's your simulation for the pocket operation. It also cleared up the island right there. Very good. Now, what's the benefit of working with an integrated CAD system? So if you make a change to your design, so let's say I want to modify the islands, I'm going to modify the height of the island in here. So I'm going to change the height of the island to 1 3/4. You'll notice that it automatically marks the operations as dirty, so you can just do a right-click and regenerate, and that'll update the toolpath, and you'll notice that now the system automatically determined the island top as being at a 1/2 inch from the top face of the part. So you can go back and run the verification again to run the simulation for it. you can always select pause and hit simulate to end to run through your simulation. Now once you have all the operations programmed, you could go over to the Setup tab, right mouse button click and select Information, and this will give you an estimated machining time for each of the operations and gives you a total amount of time that would require to mill this part. You would then right click and select Post to post-process these operations out to your machine controller. By default, the system will automatically use the name of the part and the setup name, and it will save it in the folder where the part was loaded. Selecting Post will preview the posted code in a text editor or your CNC editor right here. You can also create a shop documentation by selecting the setup, right-click and select shop documentation. This basically creates a setup information sheet which creates and lists all the operations that are programmed, so which is very useful for the machinist in the shop floor to be able to prepare your part for machining. So it lists the tools being used. It also shows the setup where your origin is, shows each of the operations that is programmed on this part. Now one of the nice features I would like to show is the interoperability between VisualCAM for SolidWorks and the standalone system. This is a brand new feature that's introduced in the 2015 version where you could export the CAD data in the machining operations what you program to a VisualCAD file format. So if you select Export to VCP, this will automatically export the file as a VisualCAD part format. So you could then go ahead and take this file and load it in the standalone system. If you have a shop floor where you only have a copy of VisualCAD CAM and you want to be able to load this part and make any changes or edits to this, you can export it and then bring it into the standalone system, and you'll notice that all of your machining operations are in here. If you want to make any design changes, any changes to the toolpath, you can just double click to edit the model in here. You can make changes to your cutting parameters, and you can do a regenerate of the toolpath, and there it is. And you can go ahead and post-process. So this interoperability gives you the flexibility to take your program part from VisualCAM from SolidWorks into your standalone system if you want to make some quick changes. Let's say you want to change your feeds and speeds or the parameters and repost it, so you don't have to go back into SolidWorks. So at the shop floor you can make this edit and then post it out to your machine tool. So export to VCP is available with the bridge license for VisualCAM for SolidWorks and VisualCAD CAM standalone. Folks, the next thing I would like to demonstrate is some of the very nice toolpath methods and new features that are introduced in 2015. So I'm going to go ahead and bring in an example to demonstrate high-speed pocketing in VisualCAD CAM 2015. So I'm going to go ahead and bring in this example in here, which will demonstrate high-speed pocketing. You'll notice that I got a part loaded in here which has several pockets on it, and the high-speed pocketing method can be found under 2-axis and high-speed pocketing. Now this method, high-speed pocketing, creates toolpaths with constant cutter engagement, and the toolpath is formed in terms of tangential arcs. So basically the benefit of this is you can run it at higher feed rates with constant cutter engagement, which basically prolongs your tool life and saves you, total cost savings, basically results in cost savings. So you can see the toolpath. I'm running the simulation here. It starts out with a spiral cut and then creates a toolpath with a constant tangential arcs, results in constant cutter engagement, so which can run the toolpath at much higher feed rates and prolongs your tool life and reduces machining time. So here's your high-speed pocketing toolpath. There are several other methods available in 2-axis, like you have V-carve roughing, V-carving, engraving, chamfering, hole pocketing. Hole profiling is a brand new method that's introduced in 2.5-axis, and we have for thread milling, T-slotting, and remachining. Now let's move on to some hole feature detection method, and then we'll take a look at some of the 3-axis, powerful 3-axis toolpath methods in VisualCAM for SolidWorks. I'm going to go ahead and bring in a part in here to show you the power of hole feature detection for drilling operations in VisualCAD CAM 2015. Now I got this part loaded in here. You'll notice that the part has several hole features on this model. You can see some counterbores and through holes on this part. Now let's see how well we can detect these features and automatically program these. Now, if you notice in the Machining Objects browser, there's a tab called Features. So we're going to click on the Features tab, and we will go ahead and select what's called Create Whole Features. So I'm going to click on Create Whole Features, and I'll pick the top face of this part and accept the selections. Now, VisualCAM automatically detects these whole features. You'll notice that there are two types of whole features detected. So one's for this counter bore, and there's one for the through holes. And when you expand the whole feature list, you'll see that there's a total of 8 instances of the same whole feature being identified on this whole feature number 2, as well as the same 8 instances for whole feature number 1. Now, I already have a set of machining operations that are defined and saved in the knowledge base for one of these whole features. I'm going to click on this button called Select Matching Knowledge Base and create whole feature machining operation. When I click on it, the system will automatically create those machining operations for the whole features. Now I'm going to go back and show you how I got to this point and how I created these knowledge base. Now, one of the benefits of doing this is if you have whole features on a part that have exactly the same whole features, but the parts are of different sizes or different shapes. So let's say you're working on a part which basically have the exact same whole sizes and whole features, but the parts are different. You can create these knowledge base of these whole features and program them. So you can here you can see that when I clicked on Select Matching Knowledge Base and Create Whole Features, it automatically created these 3 operations which I had predefined. So I had created a sequence of operations for center drilling, deep drilling, and hole pocketing, and you can go back and change these parameters and anytime. So what we're defining is a sequence of operations to be programmed in this knowledge base. I could now go to the Simulate tab, and I'm going to run a simulation in here. So I'll go ahead and display the part geometry, and I'm going to create a stock material in here. We'll do a cylinder stock about the Z-axis, and let's go select the operation and then hit the play button. You can see that the spot drill operation, the deep drill, and then we're going to run a hole pocketing operation in here. Now let's go back and learn how we created these whole feature knowledge base. So as you select the whole feature operation, the whole feature in the tree, you could click on Create Whole Feature Machining Operation. Now this displays a dialog which displays the whole cross-section of the detected whole feature in here, and then you can pick the operations that you like to use for programming it. So let's say, for example, you want to start out with a spot drill or a center drill. You can drag this operation over from the available operations to the desired operations. Next, you may want to do a deep drill operation. You can drag it and drop it. And then let's say you want to do a hole pocketing. Drag it and drop it. Now, as you select each of these operations, you can also set the top and the bottom Z values, meaning the depth for each of these holes. I can make a change in here. So I can also go ahead and specify a depth. I could say for the center drill, I only want to go down to an 1/8 inch deep. For the deep drill, I want to go all the way through. And then for the hole pocketing, I can pick the depth all the way up to the counter bore, and then I can click on Create Whole Feature Mopset, or I could also save this to a knowledge base in here. So when you click on Create Whole Feature Mopset, this basically creates the operation and lists them in your machining browser. Now we can switch back to your Tool tab, and you can choose what tools would you like to use for it. So for example, for the center drill and deep drill, I would like to use a 1/4 inch drill. So I can select the drill tool and just drag it and drop it on top of the center drill operation, and repeat the same step for the deep drill as well. And for the hole pocketing, I would like to use a 1/4 inch flat mill. So I can select the 1/4 inch flat mill, drag it, and drop it on the operation. Now we could perform a right mouse button click on it and select Regenerate, and all of your whole feature operations are generated. You could then save these operations out to a knowledge base, and then once you save them out to a knowledge base, you could basically use these on other files which have exactly the same whole features, and just with the one single button click, you can create all of those machining operations. Folks, if you do have any questions, feel free to ask them in the in the questions panel, and we'll try to get to them as quickly as we can. Next, I would like to go ahead and demonstrate the powerful 3-axis machining methods that are offered in VisualCAM for SolidWorks. So I'm going to go ahead and pull in this part in here, which has several sculpted surfaces and other features on the model. Here you go. Now the part we have loaded here has several features where you can see some drafts in here. You have some fillets. You have sculpted surfaces on the part. So parts like these would require you to program in 3-axis. Now the workflow is very similar to what we did for 2-axis operations. So the machine type will set it to 3-axis. In the next step, we would like to go ahead and build our stock material. So I'm going to pick stock and I'll select box stock in here. And for the stock dimension, I'm going to say copy model bounding box, and it will increase the stock height to 3 3/4 of an inch. And then I'll pick OK, and the stock is now defined, and you can click on Show Stock Visibility to display the stock. In the next step, I would like to specify my warp 0, so I'm going to pick warp 0. I'll set the 0 to the stock box. We'll pick highest Z for the 0 face, which is the top face of the stock, and I'll pick the southwest corner and then pick Generate. So this basically establishes your warp coordinate 0 or the program 0 to the top face of the stock and then the southwest corner. Next, I would like to program my toolpaths. I'm going to start out with the roughing toolpaths. I'm going to go to 3-axis milling, and you'll see that VisualCAM offers a wide range of 3-axis methods, starting with roughing, re-roughing operations. We have several different types of finishing methods. We have methods for additional finishing like pencil tracing, remachining, flats machining, steeps machining, radial spiral machining, machining between curves, curve-based machining. So we'll start out with the roughing toolpath in here. So this is the most common way to rough it out. So once we select the roughing operation, it automatically displays this dialog where you can specify what features would you like to rough. Now by default, VisualCAM will automatically analyze the part and the stock geometry to determine the areas that material needs to be removed. So we'll skip the process of selecting control geometry. We'll go to the tool definition. We'll select a 1/2 inch end mill. For feeds and speeds, we'll use load from tool, and clearance, we'll set it to automatic. In the cutting parameters, you can specify your tolerances, the stock allowance, the amount of stock you wish to leave. You can pick your cut pattern, specify your step over. We'll do 40% of the tool diameter. In the cut levels, you can specify the step down parameters, and you can also have additional control to specify how far down you want to cut. So let's say I want to leave about 1/2 inch from the base of the part in here. I can specify how deep I want to cut. Either I can use the pick button in here to go pick a point on the model right there, or I could even type it in, enter in a number, say I only want to go down to 3 1/4 inch. And then I'm going to pick Generate. In this process, the system will automatically analyze your part and the stock geometry and automatically figure out your toolpaths. You can see how fast the toolpaths were computed. Your toolpath is now displayed on the model. You can also view the toolpath as it steps in levels. So this is basically known as horizontal roughing, or also known as roughing in levels or Z-level roughing. I'm now going to switch to the Simulate tab and quickly run the simulation. So I'll use one of the other simulation models called the voxel simulation model, which is included in all our product configurations. And I'll set my simulation accuracy to fine in here. And let's go back and run the simulation. So we'll pick the operation and then hit the play button, and there's your material removal simulation right there. You can also slow down the simulation by using the controls in the simulation tab to run the simulation. Either you want to run it slow or fast. You can also hit the pause button and select simulate to end to run through your simulation. So there's your roughing simulation. You can see that it's roughed it down in levels and brings it as close as possible to the shape of the finished part. Now let's go ahead and program a finishing toolpath for this part. Now I'm going to go up to 3-axis and we'll select parallel finishing. Now for the control geometry, again, if you do not specify any machining features or regions, the system will automatically compute the toolpath based on the entire part geometry that's built. Now I would like to contain the toolpath, so I don't want to go past on the back of this part. So what I'm going to do is use select flat area regions. I'll just pick the bottom or the floor of the part in here, bottom face of the part. So I would like to keep my toolpath within this area. For the tool, I'm going to switch over to the ball mill, or I could even do the corner radius tool. In the cutting parameters, I'm going to set my step over to be 15% of a tool diameter. I could even use distance or a scallop height. For the angle of cut, I'm going to use 45 degrees and then pick Generate. So now this creates a parallel finishing toolpath where the toolpath runs in parallel planes, and since I chose the angle of cut to be 45 degrees, it will be running at a 45 degrees to the x-axis. So if you take a look at the simulation here, the toolpath shows the material removal simulation, and there's your toolpath. being displayed. It's following the 3D geometry. You can always select pause and pick simulate to end to run through your simulation. So there's your 3-axis finishing toolpaths. Take a look at that, how nice and clean it looks. And take a look at your 3D finishing toolpath following the 3D model. Now you'll notice that based on the toolpath and the step-over parameters you used, you may see some scallops that are being left on these areas in the model. So you can use methods like 3-axis pencil milling or pencil tracing to go ahead and clean up those features. Again, if you want to specify a containment, you can pick that. In this process, I'm going to skip the selection of containment. We'll use the same tool and then pick generate, and it'll automatically analyze the part for bitangencies and create a toolpath to go clean up those areas. So this is a big time saver. Saves you amount of time that requires you to go back and manually do cleanup and finishing on these models, especially when you're working with metal. You know, the pencil tracing and remachining are great toolpath methods. You'll now notice that the pencil tracing automatically goes and identifies those bitangencies in the part and creates a toolpath to clean them up. So VisualCAM offers a powerful set of 2- and 3-axis milling methods for your machining needs. Now, if you want to go back and program specific areas in here, we can define areas to contain the toolpath. So we could go to 3-axis, and let's say we want to do a radial machining, and I can go pick a specific area in here. So we'll do a right-click and say select tangency, so we can pick these areas to generate a toolpath for. And we'll accept the selection. We could pick a different tool. So let's say you want to go from a 1/2 inch ball to a 1/4 inch ball, and then pick generate, and there's your radial finishing toolpaths. So that's how we can select areas to machine and program toolpaths. And once you have the toolpaths programmed, you can look at the estimated machining time. So right-click and information will tell you an estimated time. And saving the part in SolidWorks automatically saves all of your machining data or the CAM information to the existing SolidWorks part document. Once you have the toolpaths programmed, you can go ahead and do a post, which will post-process the toolpaths out to your machine controller, depending on whatever machine controller you pick, and it automatically outputs the tool numbers for each tool that you program. So if you have a machine that has an automatic tool changer or even a manual tool changer, it'll output those tool change codes in the posted output file. Now I would like to show you our 4- and 5-axis machining capabilities that are offered in VisualCAM 2015 for SolidWorks before I move on to the turning module. So I'm going to go ahead and bring in this model, which I already have a few 4-axis toolpaths programmed on it. So this is a very good example which will demonstrate both indexed and continuous 4-axis machining methods. Now here's a part that's loaded. You can see it's basically a prototype model of a water bottle. And you can see that parts like these require machining from multiple sides, as you see undercuts which cannot be machined from just one orientation. So part like these can be programmed in 4-axis. The first step you would need to do here is define your machine tool definition, where you can specify the number of axes as 4. You pick the machine configuration. If it's a rotary table, you pick table, and then you pick the rotational axis, whether the part is rotary axis is established or set up about the X or the Y axis. Once you establish the machine definition, you can program this part using a combination of indexed and continuous methods. Here we are programming a roughing toolpath using indexed operation. We are roughing it from the top, and then we are rotating it by 180 degrees. So basically the rotary table rotates 180 degrees, and you can program a roughing operation for the bottom half. Then we can rotate the table back and program a continuous 4-axis toolpath. I'm going to run a simulation so that you can take a look at how the finished part would end up after being programmed. So let's go ahead and switch the simulation model. So we would need to use the polygonal simulation model in here to be able to simulate undercuts or simulate for multi-axis programming. And I'm going to select that, and we'll go ahead and run a simulation for the roughing toolpath. So I'm going to hit the play button in here, and you'll see that the part is rough, and we limited the Z just to go halfway down, so you can flip the part over. So the part gets rotated over on your machine tool, on your rotary table, and then you'll be able to rough it from the other side. So I've also added some supports in here so that the part doesn't go all the way to the ends. And the next step I'm going to do is program a continuous finishing toolpath in here using a 4-axis and parallel finishing. So the part rotates on your rotary table as the finishing toolpath is being programmed. So this is how we can program parts effectively using our 4-axis methods. We offer both 4-axis indexed and continuous 4-axis toolpaths. Now there are several other types of 4-axis methods available, which you can access all of these methods by going over to the Program tab. Under 4-axis, you'll find access to all of the methods like 4-axis spacing, pocketing, profiling, finishing, 4-axis pocketing, and engraving. Now for index programming, you would be using basically rotate table setups and program a combination of 2- and 3-axis operations to program index 4-axis. Next, I would like to now demonstrate our 5-axis capabilities in VisualCAM for SolidWorks. I'm going to bring in a model here which will basically demonstrate some of the 5-axis toolpath methods. So first, I'm going to be programming a roughing operation in here using a 3-axis roughing method. So I'm going to show you these operations here in the machining browser. You'll see that's a roughing operation. And let's go ahead and run a simulation for the roughing operations. I'm going to pick simulate to end. And you'll notice that the part is now roughed. The next step, I'm going to show you how to program a 5-axis toolpath. So if you go back to the Program tab, you'll have access to all of the 5-axis simultaneous methods under the 5-axis pull-down menu under the group called Machining Operations. And here we programmed a swarf machining operation in 5-axis. Now we can also program index 5-axis using a combination of coordinate system setups and using 2- and 3-axis operations. Here what we programmed is a simultaneous 5-axis operation. And let's go run a simulation in here. And you can see that the tool axis orientation changes. This basically total of 3 linear axis and 2 rotational axis, and what we're programming here is a swarf machining. So VisualCAM mill module offers 2- to 5-axis milling solutions, and these are available in different configurations: standard, expert, pro, and premium. For more information about our product configurations, visit our website or feel free to contact us, and we'll be more than happy to provide you with more information. Now I would like to demonstrate our turning module. So I'm going to go ahead and bring in a part so we can show you how you can use VisualCAM for SolidWorks to program parts on your turning centers or your CNC lathes. So let's go ahead and bring in a file, and we'll work on a turning example in here. So I got this part loaded in here, and in order to switch from the milling browser to the turning browser, you can either click on Turning Browser under the VisualCAM's 2015 tab in the Command Manager, or you can click the button that says Mill to toggle from mill to turn right in your machining operations browser. So we're going to switch the interface from mill to turn, and you'll now notice that the interface automatically switches over to the turning module. The first step in here is to define the orientation, the machine tool coordinate system orientation. By default, VisualCAM's turn module orients your world x-axis in SolidWorks to the turn z-axis, and then the world y-axis to the turn x-axis. If you need to change the orientation based on how your part is modeled, you can use these controls in here to establish your orientation. Next, we would like to go ahead and define the post-processor. The turn module offers a handful of post-processors in here, and I'm going to pick Fanuc as my current post-processors. Additional post-processors can be created by selecting the Edit button, or you can also modify to modify an existing post-processor. In the next step, we would like to define the part in here. So you click on Part, and then you can click on Select Surfaces, or you can even pick Sketches in here. Since we already have a solid model designed in here, I'm going to use Select All and accept it. So my part is now being defined. When I hit Save, you'll notice that the part is now defined, and the system will automatically create a cross-section or a silhouette of the part geometry that you selected for defining your turn part geometry. In the next step, we would like to go ahead and define our stock material. So we click on Stock, and we can choose from the available stock types. I'm going to pick a cylinder stock, and I would like to specify my radius as 1.5, and I can also set my length. And then we'll pick OK, and there's your stock material. So you can click on Stock Visibility, to display the stock. In the next step, you would want to align your stock. So in this particular step, I'm going to align it to the rightmost face of the part geometry. For Z alignment, I'll pick right face and then pick OK. You can select your material. We have a material list that you can pick from, so I'm going to pick aluminum 6061 and pick OK, and then I can click on texture visibility, which basically displays the texture of the stock material. So when you go to the Simulate tab, you can view the stock with the texture on it. Also, for the stock display, you can either display the stock as a full or a 3/4 view. So when you're programming parts that have ID operations, the 3/4 view might be a good option to pick, so you can see the simulation for the features that are being programmed on the ID as well. Now let's switch back to the Program tab and let's define our work 0. Typically in turning, the work 0 is set to the rightmost face of the stock plane, so I'm going to pick Set to Stock and Rightmost and pick Generate. Now this could be your G54 or G55, which could be your Program 0 or the work coordinate origin. In the next step, I would like to program my toolpath. So I currently have a few tools defined in here, so you can define additional types of turning inserts by selecting Create Edit Tools from the Tools tab. Define your type of insert. You can specify the orientation, whether you're cutting for OD or ID, and the orientation of the insert, whether it's going to be forward cutting or backward cutting for OD, forward or backward. You can specify your material properties and feeds and speeds. You can set them to be in IPM or IPR. You can also choose between CSS, a constant surface speed, or CRS based on how you'd like to be programmed. So the next step, I would like to program my toolpaths. We have turning toolpaths. We have roughing, finishing, groove finishing, follow curve, threading, and parting off. So first I would like to program my roughing operations. I'm going to pick turning and roughing. I'll pick the tool that's oriented for OD since I'm interested in first programming the outer diameter of this part. For feeds and speeds, I can say load from tool. Global parameters, I can specify my approach type. So based on the tool orientation that you pick, the system will automatically limit it to OD or front face for the approach type. Since the tool what we selected is an OD or outer diameter oriented tool, you can specify your tolerance, your stock allowance, and then you can specify your parameters and your turn roughing. Your entry and exit can be set right in here, and when you pick Generate, the system will automatically compute your roughing toolpath. Now there's your roughing toolpath. You can switch over to the Simulate tab and pick the play button to run a material removal simulation. You can also toggle on the texture visibility and then go back and run the simulation here. You can simulate it with the material texture being visible. Now you'll notice that it was also able to program this groove area on the toolpath. If you'd like to contain the toolpath to avoid this groove from being programmed, you can edit the operation in here, and the global parameters you can pick what is called avoid section, and you can say you want to pick a section to avoid. I can pick an edge between these 2 points, and I can hit Generate. Now you'll notice that it automatically avoids that groove from being machined. So that's how you can specify avoid sections and containment areas in turning process. I would now like to go ahead and program a finishing operations. I'm going to go to turning and finishing, and we'll use the same tool. In the finishing parameters, I can specify any stock allowance. I can pick my start and end points in here. So I want to pick the start to be right over here and end all the way to the back of this part. So I'm picking 2 points to define my start and end. And if you'd like to do it in multiple passes, you can pick multiple passes and then select Generate. And there's your turn finishing operation. Again, if you want to avoid this section in here, you can edit the operation and pick avoid sections. And there's your simulation for the turn finishing operation. Next, I would like to program the ID feature. First, I want to do a drilling operation to bore a hole on the part. So I'm going to pick hole machining and drilling. We'll use the 1/2 inch drill. And for the cutting parameters, I can pick the depth by just picking 2 faces, the top front face and the back face of the part. And if you wanted to make it a through hole, you pick Add Tooltip to drill depth and pick Generate. And the drilling is always done axially along the Z-axis, and there's your drilling operation. If you want to use a deep drill or a pet drill instead of a standard drill, you can just go back into the operation and change the type of drill from standard drill to deep drill and generate the toolpath on it. Now let's go ahead and program a roughing operation for the ID. So I'm going to pick turning, roughing. We'll pick the tool orientation as turn, insert, ID, and you'll notice that in the global parameters, the approach type is automatically set to ID. You can now specify your parameters, your turn roughing parameters, the entry and exit. The orientations or approach motions are automatically set based on the approach type. Now we'll pick Generate, and there's your ID roughing toolpath. And similarly, you can also program a ID finishing toolpath to finish the programming of this part. So once you have the part programmed, you could look at the estimated machining time by selecting information. You could also generate a shop documentation, very similar to how we did on the milling module. So right-click and select shop documentation, and you can specify from the available template types, and the templates can also be customized. And once the shop documentation is generated, it'll automatically preview it in your HTML viewer. So this basically provides you the part setup information, the total number of operations involved, lists all the tools and the operations with the time estimate for each of these operations. Again, the export to VCP feature is also available in the turning module as well. So you can select export to VCP. It'll automatically export the CAD geometry and the machining operations to VisualCAD format, so which can be then loaded in the VisualCAD-CAM's standalone module. We would now like to go ahead and post-process these toolpaths. Right mouse button, click on the operation, or you can right-click on the setup or even on the machining job and click Post All, and this will automatically create your posted output file, and there it is. So folks, this basically gives you an overview of VisualCAM's milling and turning module for VisualCAM 2015 for SolidWorks. VisualCAM 2015 for SolidWorks is a gold certified CAM partner product and runs inside of SolidWorks 2010 to 2015 and is available in both 32 and 64-bit platforms. I would now like to turn this over back to my manager, Anita, who will be able to provide you with additional information.
Thank you, Uday, and thank you everyone for taking time off your busy schedules to join us this morning. Now we are available, we have a few minutes here, about 10 minutes, where we open up the presentation for questions. Anyone there with questions we can answer? Uday is available, Joe is available, and I'm here. Having Joe around is special. He is our project manager and can give you a lot of in-depth information.
Well, hello everyone. Can you hear me?
Yes, we can hear you loud and clear, Joe.
Good. Okay, this is Joe. So yeah, we are more than happy to answer any of your questions. If you have any feedback on the product or any feedback on future direction where you want to see the product go, we'll be more than happy to entertain any suggestions as well.
Uday, since we're waiting for some questions here, are there any questions that you as a support manager can share with our audience? Something that's commonly asked of you.
You know, one of the things I want to emphasize in this product that we just released, some of the new things we added, and also as a segue into some of the things we're working on, we are starting to look at more automated machining. And one of the things that you saw in Uday's presentation was the automatic or feature-based drilling methods. I'm not sure if, you know, by a short, brief demonstration of that, you know, functionality, we're able to observe some of the ramifications of where we're going with it. So basically what we've done there is feature detection for holes and also automated single button click machining of these features, of these hole features. It's a small step towards, you know, full feature-based detection and machining. And those are some of the things we're working on. So we'll stay tuned, and we'll be able to show you some progress later on down the year. So. There is a question Uday about whether VisualCAM 2015 will run in SolidWorks 2014. You want to take that?
Sure, I will. Sure, I will. Thank you, Joe. Yes, it does. VisualCAM 2015 for SolidWorks is certified to run in SolidWorks 2010 all the way to 2015. So I'm going to load SolidWorks 2014 here. I also have copies of both 2014 and 15 running on this machine. So you'll notice that VisualCAM interface will automatically appear inside of SolidWorks 2014 as well. So as you open up a part in SolidWorks, you should be able to see that VisualCAM 2015 appears right inside of SolidWorks 2014 as well. And if you have parts that require programming from multiple sides or multiple orientations, you can use these fixture offset methods using creating additional setups to program from multiple orientations. So here is a part we programmed it in SolidWorks 2014, running VisualCAM 2015 for SolidWorks. I hope that answered your question.
We had a nice question here that I think would be good to share out aloud. There's someone who uses both SolidWorks and Rhino Uday, and he was wondering how the VCP export helps him use both products, RhinoCAM to machine SolidWorks modules.
Maybe I can take that question, Anita. As far as the interoperability, our design was to help people work with our standalone product. Have a plug-in product, and work that together with the standalone product. We have not designed an interoperability between plug-in products. The idea being that you typically, our customers would typically have a mainline CAD system, which is probably SolidWorks in this case, and then they would want a CAD or CAM system on the shop floor, which is a much simpler system for shop floor machinists or even programmers to handle. So that is the philosophy behind our interoperability design, and it does not allow you to work between plug-in products. So you will not be able to take a model from VisualCAM for SolidWorks into RhinoCAM.
Joe, there's another question that you could. Before I ask that question, Uday says he wants to add a little something to your explanation, Joe.
Sure. Yeah. Go ahead.
One of the things you could do is you can take the CAD model into Rhino, and you can export all of these machining operations, what you program, into a knowledge base. So the machining operations are interoperable between our different plugin products. So you can save all of the machining operations to a knowledge base, and then you can import those knowledge base into your other VisualCAM system, VisualCAD Standalone or RhinoCAM, and then use those operations to program the parts. So the machining operations in the tool library can be shared between our other plugin products.
Yeah, the only caveat between saving just knowledge bases and moving it to another plugin system like RhinoCAM is you will not be transporting either the toolpaths or any of the selections. So you will have to redo that in the CAM system. But while the VCP, you don't have to do any of that. The selections will already be transferred, and so will the toolpath. Hope that clarifies that question a bit.
Yeah. Joe,
there was a question about somebody using CAMWorks and the ability to pick a sketch geometry to set the work zero. Can you take that?
Sure. So to determine a work zero, I can actually model a sketch in here. So I'm going to put a sketch on this model. I hope everybody's able to view my screen. And I can go to my work zero. And I can say pick, and I can just use the pick, and then just go pick this point right there on the sketch. And that allows you to establish the work zero.
Joe or Uday, there was another question about the transfer to the VCP. There's a gentleman asking, if you transfer to the VCP and make a change to the original part, is it easily transferred back to the solid file, or does one need to go into SolidWorks and make the edit there also?
Uday, want to take that?
Sure, I will.
Sure.
So exporting it to
VCP exports the CAM data and the CAD information to VisualCAD format. So any changes that are made in the VCP format cannot be imported back into SolidWorks because VCP files are native to VisualCAD CAM and cannot be loaded or imported in SolidWorks. So you'd have to basically go back and
make those changes inside of SolidWorks once you made those changes in the VCP file, if you made those edits in the standalone system.
Okay, we do have another question here that someone's asking, Uday or Joe, can you machine from surfaces?
Yes, yeah, definitely. I mean, one of the things that they showed in the 3-axis was, you know, a whole bunch of faces, and you can machine definitely from free-floating surfaces, import a geometry, and quite a bit of other things. So we truly work with, I mean, in the case of SolidWorks, obviously you have solid models and surfaces. We can machine those. In our other products, we can also machine meshes directly as well. I hope that answers the question, Josh.
Any more questions we can work with? Yes, there's one here. Do I need a separate license to use the standalone VCP files on my shop? I have RhinoCAM presently. You have a RhinoCAM license presently. Yes, you do. What you don't need to purchase a separate license of the product all over again. We offer what we call the bridge license, which is a fraction of the cost of the product price. So depending on the configuration you're running, you can purchase a bridge license that will allow you to use this interoperability function. We have a couple more minutes, folks. Okay, sounds like we run out of questions to answer live, but we are available via email or the phone line to contact us after this demonstration to answer any questions. We are recording this webinar. It will be put up on our website. As soon as it's available, we will send an email with a link for you to go back and review this session. I thank everyone who's taken the time off your busy schedules to attend this session with us. Uday, thank you very much. That was a very nice presentation. A lot of information, as always. You like to pack in a lot of information within that 45 minutes. So thank you. And Joe, thank you very much for joining us today and helping our viewers with all those questions.
No problem. I just wanted to add that any feedback, any of your customers who have experience with our product already, we would love to get your feedback on the product itself, and then how do you want the future direction of the product to go. So that we'll be more than happy to entertain those things. Thank you very much.
Thank you all. Until next time, take care, folks.
Bye-bye.